Yeah, welcome everyone, right, to our blockchain at UBC monthly research talk. If you still remember, right, we have already a long history. The blockchain at UBC was established about 10 years ago. So this summer, we will have our 10th anniversary, like a summer institute. Maybe just a quick preview, right? It will be August, and we will talk about many interesting topics for the latest developments of Bitcoin and blockchain technology. As blockchain at UBC Research Center, right, our unique focus, even from day one, was on this multidisciplinary style. Right? We want to combine researchers from computer science, engineering, like a business school, right? Sometimes medical school, like law school, and to do some exciting projects with some potential real world impacts, right? This is our philosophy, and we had some success stories are shared on our blockchain UBC websites, and maybe you can check out if you haven't. Next, I will introduce our speaker today, Chris Blake. Right, he is he's a professor with the Great Bay University, a kind of almost brand new university in China, which would like to modern, right, this North American style. So this is hello, and this is we call it like next generation, right? Like research-oriented universities in China. And Chris is also my longtime friend, right? And we spent several years at the University of Toronto. So a quick background. He did his bachelor's degree, right, at University of Toronto, and also learned Mandarin very well. More stories to come.
Mandarin Chinese, the language.
The language, Mandarin, right, during his undergraduate studies. And then he moved to MIT for his master's study on quantum communication, right? And keyword number one, quantum. And then later on, he missed the Chinese food and the Chinese friends. And so right, he came back to U of T doing his PhDs and on information theory and coding theory, right? Some fundamental limits. Because at that time, I was his academic big brother, right? So that's why I kind of knew his style and his research work. Maybe for the sake of time, right? Maybe just one sentence summary. A UC Berkeley professor spoke highly of his PhD thesis, right? Something like if this thesis war right at UC Berkeley definitely has the potential to receive some PhD thesis awards, so like award-winning level. And after his PhD, because as you will say, Chris was very curious, like many great minds in the history of science. After his PhD, he did some machine learning research, right, in AI lab in Toronto. If you still remember the deep learning revolution, right? Golden time. And
Say this
I know.
machine learning stuff.
Yeah.
It's not slowing down.
And then then we had this maybe a blockchain revolution, right? So Chris spent some time doing research with a top blockchain project. I think if I remember correctly, he was even invited to be a head of research, right? One time, yeah. So no, back to right, and then he did some startup and many other activities because he wanted to live a full life, right? Trying out different things. And very recently, I like recommended, right, and him and to this like brand new university, and he believed it was a very interesting opportunity, right? That's why he joined the Great Bay University. So as you can see, his background is very broad, covering quantum, AI, blockchain, right? And both from theoretical perspective and from like a practical perspective, right? Working.
Information theory. That's probably like the core,
Yeah,
my core
this is
specialization.
exactly what I'm about to say. But across all those different kind of application scenarios, underlying is the core like theoretical tools from information theory and coding theory. And today, Chris will apply, right, share with us about how to apply these tools, right, to kind of reason about Bitcoin-like protocols, and in particular, how to make it more secure. And this is right, like very important nowadays because we know Bitcoin has several kind of attack surfaces, right? If it wants to go mainstream, right? We need to have a deep understanding about different attack surfaces. So welcome to Chris for this talk. Thank you.
So thank you for the intro. I hope that the few people who are watching us online, you can hear and see us. But if so, comment that you can. And if you can't, I guess that's too bad then. Because I won't be able to hear you or comment. Okay, so making Bitcoin more secure by merging hashing resources. This is work that I've done with Chen, and I've actually worked on it for a number of years. And I'm also working on with my collaborators at Hong Kong University of Science and Technology, Guangzhou campus, which is nearby where I live, which is in Dongguan. For those who don't know, Dongguan is a city, a small city of 10 million people in China that many have never heard of. Not small, but it's, well, for Chinese standards, it's considered, it's not well known. Although in China, people know about it. And it's sandwiched between Guangzhou and Shenzhen. If you've heard of these two very big cities, there's another big city about the same population. And it's one of the manufacturing hubs of the world. So if you have any item at all of any sort, it very likely came through Dongguan and someone there manufactured it. So this talk, of course, is about Bitcoin, as you all know, which was created by Satoshi Nakamoto, who is legendary because we don't know who it is. Now, I wonder if the person who wrote the Bitcoin white paper actually gave the real name. I wonder if it would even have the same mystery or the same success. But it's one of the most famous pseudonymous or anonymous contributions to science in the world, I think maybe that has ever happened. And it's part of the mystery of it all. So what is Bitcoin? Bitcoin is a distributed ledger backed by proof of work. We'll get to what we mean by that in a second. And importantly, with Bitcoin, there are two types of agents, miners and transactors. Transactors are constantly submitting digitally signed transactions to the protocol, like move 3 of my Bitcoin from this account to this other account. And they use a digital signature to ensure that they really meant to send this. And then the other agent in the Bitcoin protocol are the miners. The miners are those keeping track of this database. But they perform this proof of work computation in order to secure this blockchain. So what is a blockchain? Well, a blockchain, okay, being recorded. Here we go. Wait a minute. There we go. Okay, blockchains are a data structure. A block contains a bunch of these digitally signed signatures, and a value of a nonce, which is just some number, a number that's a guess, so that the hash of previous transactions nonce is less than some threshold, which is set by the protocol. Previous is a hash of a prior block. And just as a side note, which will be important for our talk, the particular hash function used with Bitcoin is called SHA-256. Nothing fundamental about that other than it just happens to be SHA-256. So we can see here's an illustration of a blockchain, a data structure that contains a whole bunch of transactions and critically the hash of previous transactions nonce. So when mining Bitcoin, everyone in the protocol must be constantly collecting transactions, checking their validity, composing a block of transactions, and constantly testing hash of previous transactions nonce. When hash of previous transaction nonce is less than some threshold, the miner is to broadcast that block as well as the nonce value that makes hash of previous transactions nonce less than the threshold. And then the miner grants themselves a predetermined block reward for doing this. So in fact, you might say that the block reward is always in transactions and hash of previous transactions nonce as the miner is searching for the right value of a nonce that gets us below the threshold. So in addition to mining for the next block, for the next Bitcoin, miners are also constantly collecting previous blocks that have been broadcasted and verifying them. By verify, what we mean is the miner must check and make sure that all the transactions are valid and that the hash, the hash from hash of previous transactions nonce, to make sure that that hash of previous transactions nonce is less than some threshold. And a transaction is valid if these two conditions are met. First, all the digital signatures must be authentic. And no balance in the blockchain goes negative. And the block word has to be correct, which is set according to the protocol. So I did it. I made a slide, hash of previous transactions nonce. The reason I made this a slide is because if you want to remember what Bitcoin is, just remember this. Hash of previous transactions nonce. The computation of Bitcoin is overwhelmed in complexity just by doing hash of previous transactions nonce. 1 trillion of these computations and a few thousand other computations is what a Bitcoin miner will be computing. Hash of previous transactions nonce. So the question you might ask then is that, okay, well, if we're computing hash of previous transactions nonce, how do you decide what previous is? That's a question. Because we're always running, or miners are always running collecting current proposed blocks and verifying subroutine. But in principle, there can be many potential previous blocks, which is especially true if there are adversaries trying to mess up the consensus. So we need to have some kind of rule to figure out, given all the potential blocks and all the potential blockchains, what is the block you're supposed to mine upon? That thing you plug into previous of hash of previous transactions nonce. And the rule for deciding what to mine upon is called the fork choice rule. And here's the Bitcoin fork choice rule. Mine on the tip of the longest valid chain. Very simple. So in this case, in this illustration, potentially, you could have presented to you a blockchain that looks like this. The fork choice rule in this case is to mine on this block, the block that's at the tip of the current longest chain in all the chains that exist. by the way, okay, just a side note here. Because Bitcoin, and specifically Bitcoin, has been run for so long, and it is the biggest blockchain by far, you can almost say that the Bitcoin fork choice rule is to mine on the tip of the longest valid chain that exists in the universe, that you can see anywhere on Earth, like anywhere, no matter where you get it from or who gives it to you. Bitcoin, and only Bitcoin, is the protocol that always mines on the tip of the longest chain that could possibly be presented to you. Okay, now to construct another chain to compete against Bitcoin, you'd actually have to expend enormous amounts of resources. And might not be plausible to do that. So it's not just necessarily the longest chain that starts at some particular block or the longest chain part of like what you know to be the Bitcoin structure. It's at the longest chain that exists, but that only works for Bitcoin, because for everything else, Bitcoin's a longer chain. Well, for everything else, like if you have another blockchain algorithm, if I were to say to you, just as a side note, well, mine on the tip of the longest chain that you see presented to you, okay, well, if it's not Bitcoin, it won't be longer than the Bitcoin chain. So it's not the longest one that exists. But currently, the Bitcoin blockchain is the longest linked chain of hashes that exists, like that exists in the universe right now. Does that make sense to you? Yeah, you have a question?
Yeah. What's the longest? Yeah.
Okay, you look at it. You look at it and you count the blocks in it. Okay, so generally what you'll be doing is you'll be asking, according to a protocol, for all the miners to please broadcast me the current state of the blockchain. And they will broadcast you something that may look like this, much bigger now, of course. Okay.
Block has a number, right?
But longest is
Find the one.
well, you mine on the one, so every block has transactions and hashes and everything, but the rule is that if they're all linked up, right?
Yeah.
So the rule is to mine on the one block that has the longest chain of links in it.
Whole block history.
The longest history of links, that's the canonical blockchain. That's what we call it the canonical blockchain. Okay, so how do you know it's the one? It's because you can look at all of them and then see which one's the longest. Okay, but now it does require you to see all of them. Okay, but there's a way that you can ask for that to be broadcast to you, and then you can get a proposal for what the current blockchain is.
I used to run a node only.
Oh, really?
Yeah. Long time.
Really? Good timing to do it 5-10 years ago. Like
Down the file. Right now, it's over a terabyte.
yeah.
But it was constantly getting updates from the network,
Yes.
right? I often wonder how it knew how to validate.
Well, the way you validate is well, first, the key thing to remember about Bitcoin is that not only does it work if everyone's honest, it also works if everyone except for 49% of like agents is honest. So long as 51% of agents are honest, this will work. It's the reason why you go through the whole rigmarole of having to compute this hash of previous transactions nonce. It's because it's hard to create a competitor chain that would be the longest chain. Because it requires a lot of computation, a lot of computing these hash of previous transactions nonce. You have to do trillions of them to get the next block for that hash to be below a threshold. Yeah, well, you can have a blockchain with like, you know, a different structure or with different hashes. It's just that like it won't be a longer blockchain it won't be a blockchain that's backed by more hashes or proof of hashing than any other alternative. And you could, in principle, you could have a longer blockchain, but it will be one where the hashing threshold is lower complexity. Or in principle, you could have a more popular a blockchain that becomes more popular than Bitcoin, and then that would be longer too. But that's a side note. Okay. Any other questions just before we go on? Okay. So This is our setup. Okay, mine on the tip of the longest chain, collect all the transactions, compute hash of transactions previous nonce. And if you do that, okay, I didn't say anything about how this works other than this is what you're supposed to do. But if you do that, there's a security guarantee that we can claim, okay? But it's parameterized by these variables. If we let H be the honest block rate, okay, so once you have a bunch of computers computing hash of previous transactions nonce, then that induces a particular rate of valid blocks. Okay, so there's some block rate, blocks per second or blocks per hour or whatever you call it. And if you have an adversary, fixing the hashing resources for the adversary, there's going to be some fixed block rate B for the dishonest blocks. And when we say that a blockchain is secure, what we mean is that some honest transactions get through to the longest chain and stay there forever. And so we have a security guarantee. Bitcoin is secure if B is less than H. Okay, if the adversary block rate is less than the honest block rate, then Bitcoin is secure. And in the analysis of it, there's a fundamental idea of blockchain analysis. Once H and B are fixed, the hashing resources, then the arrivals of the next block in this process form a Poisson random process, which we can analyze. And the blockchain becomes a race between two stochastic processes, the adversary and the honest arrival processes. Okay, so that's a brief introductory outline of what Bitcoin is. Remember, hash of previous transactions nonce. That's the key thing. But Bitcoin now has been proposed to become the world's reserve currency. It may seem implausible, but somehow Bitcoin has a market capitalization of over $1 trillion right now. And it's maintained this for quite a while because I gave this talk like 2 years ago and it was still above $1 trillion then. So it's maintained above $1 trillion for a long time now, or it was at least close to $1 trillion back then. So if it's to become the world's reserve currency, whatever that means, right, at least it needs to be more secure. That's my motivation. At least it needs to be more secure. So can we, now remember, we said that I'm an information theorist, right? So the question I have is, can we improve the security of Bitcoin using an information theoretic approach? Now the question you may ask is, what is information theory anyways? But here, so I'm an information theorist. I thought about this, and the thing that I came up with was a simple idea. Instead of using just SHA-256 to produce hashes between blocks, we could use a combination of hashes. So Bitcoin ASIC miners can run the SHA-256 hash, trying to build upon the longest chain, while others could use a different type of hash. For example, ETH hash, which is the hashing function that was used before in Ethereum, before Ethereum was converted to proof of stake. This is inspired by a basic idea from information theory, that in information theory, independent uses of a noisy channel can provide some useful redundancy. So the idea here is that, well, maybe if we use different types of hashing resources, we can be robust against certain possibilities of types of attack. So let H1 and H2 be the honest block rates for hashes of type 1 and type 2. So for our example, we'll do a 2 hash type running example. And let B1 and B2 be the dishonest block rates. So this is what we want here. So in this graph here, we are plotting B1 and B2, and we're assuming H1 and H2 are fixed. So, and we can ask, okay, for this given H1 and H2, what values of B1 and B2 is the protocol secure? and what values is the protocol insecure. Now, in the classic Bitcoin case, let's say we were just mining using hash type 1. The security region is right here. If you can see where my mouse pointer is going, the security boundary is right here. So I'm just going to do this just to illustrate. So in classic Bitcoin, everything to this side is insecure, and everything to this side is secure. Okay. And what we would want if we're applying the principles of information theory is that we want to be secure by and require an adversary to break both types of hashing resources to require that B1 be over H1 and B2 be over H2. So it requires an and of breaking these security conditions. That was the dream, okay? That was what we hoped we would be able to do. Unfortunately, instead of proving we could do something like a true information theorist, we proved you can't do it. And we actually do this using a fairly simple inachievability result using an emulation argument, where an adversary emulates a secure configuration of block rates. And we can show, okay, if it's secure for honest blocks, then it's insecure for the adversary. Thus, if we have a particular configuration of block rates right here, H and B here, if that's secure, then our theorem can show that if this is secure, then swapping the rates is insecure. But in this case, we have that B2, so when we swap it, we have that B2 is less than H2, which if we're talking about our hoped for security region, that should be insecure. But because of our theorem, it must be insecure if the alternative is secure. So we can't do it. So though we can't get to our hoped for security region, we can still ask, can we do anything? And yes, we can. Merged Bitcoin is secure if and only if, okay, I have to tell you what C1 and C2 are. Now, if we're hashing with different hash types to create the blockchain, then there are actually different block types based on which hash was used to create the link to the previous block. Okay, so if we say that each block type has a different score, we could call blocks of type 1 to have score C1, blocks of type 2 to have score C2, and so on. And then this is our rather predictable security region for the merged Bitcoin algorithm. Merged Bitcoin is secure if and only if C1B1 plus C2B2, the adversary score growth rate, is less than C1H1 plus C2H2, the honest score growth rate. So are we done? Well, we can say a few more things. When people were analyzing the Bitcoin blockchain, they had results kind of like this, and it's fairly easy to show this using a little bit more arguments, a little bit more sophisticated than the law of large numbers. But it was later realized that if you add delta delays to honest miners, that is, if it takes a time delay of delta to get to from the time that a block is mined to when it's broadcast to all the other miners mining the Bitcoin protocol, then you can actually, it actually damages the security of Bitcoin. And the reason for that is we can see from this image here. My apologies to the people online. You can't see this, but this is a diagram of a blockchain that's growing. And from top to bottom, the blocks here occur, in the time order that they occur. And we label a delay delta after some subset of the blocks, which we're labeling G's, we're calling them guarantee blocks. And here's what happens if there is a network delay. So we call this block and the mother block. Mining is miners compute hash of previous transactions logs. Then the next block occurs. Okay. Now, as soon as that block occurs, that should be the longest chain. Okay. However, if there's a time delay of delta before the next block arrives, then these miners here, the miners who found this block and this block, don't see this block yet, but they have to compute hash of previous transactions nodes. So what are they going to plug into previous? They're going to plug in the prior block. Okay, so what happens here is that some fraction of honest blocks will not form part of the same chain, will not form part of the canonical chain. So if the network delay gets bigger, a greater fraction of blocks that are mined do not make it into the canonical chain because they mined a prior block that isn't the longest. So when you consider delta delay, things become a little bit more confusing. But we can actually, this is an interesting discussion to be had here. We can compute the rate of honest arrivals if there's this delta delay. So let's let R be the rate of block arrivals in this fully delayed chain. So some blocks get orphaned, we call it, but then there's some rate, whatever it is, it's called R, whatever that rate is. And R is equal to the rate of block arrivals, honest arrivals without delay, okay, minus those blocks that get orphaned because they occur delta after a block that's guaranteed to get through. Okay, so the rate of these fully delayed blocks is R is equal to H minus the rate of orphaning, okay, which is, well, it's the rate of the guaranteed blocks times the time delta after it, times the rate of arrival of blocks, of honest blocks in that time, which is also H. So if you rearrange it, we get a fairly well-known result for the rate of growth of honest blocks in a fully delayed chain, which is H over 1 plus delta H. Okay, let's continue. Okay, so in the case of delta network delay, we now have another security result, which is a little bit more complicated. It's this delta H, which is a function now of, or sorry, lambda H, not delta, lambda H, which is a function of the honest block rates, the delta, and the C1 and C2. This is the score growth rate of a now fully delayed chain. If that's greater than C1 V1 plus C2 V2, which is the score growth rate of a not delayed adversary, because an adversary doesn't face these delays, then merge frequent is secure. Or if you flip that around, then it's not secure. So what's interesting about this? Well, it turns out that if blocks can have different scores, so for example, maybe we think that computing ETH hash is easier than computing SHA-256. And so the score of a block mined using ETH hash, maybe we say has to be a little bit less than SHA-256 hash. If that happens, then the score growth rate is not as easy to predict. And we can see an example here. I placed a number indicating the score of a block in each of these chains here. And if you look at this one, I think you can see that the chain that would be formed with this blockchain would be A, B, C. Okay. However, that's because all of these blocks have the same score, score 1. In the case of a score, or a block having score 3, for example, when block E is 9, observe that block E occurred within delta after block C and after block B. When block E sees the chain at the time it occurs, the highest score chain now is AC. It has score 4 compared to score 2 for the alternative, changing the shape of growth of this blockchain. It turns out that if you really analyze it, it's actually rather difficult to analyze how a fully delayed honest chain will grow if blocks are of different score. So one of the main contributions of our work on this is trying to bound the rate that this grows. And so we have two techniques. For a lower bound, we have what we call the delta interval deletion process, where we consider a sequence of blocks. The first block that arrives, we call a guaranteed block. That's the first block at the beginning of this little gray shaded area. Everything that arrives within delta of that, we call it an orphan block. Okay, and so on and so on. So we get a sequence of guaranteed blocks. Then what we do for a lower bound is we just delete everything that occurs within delta of these guaranteed blocks. And we can show that the honest score growth rate will be at least the rate at which this chain grows. And when we can analyze that, if we want to, the analysis of the growth rate of this chain is a lot easier than the chain where you don't do this type of thing. And for an upper bound, wait, where are we? Yeah, for upper bound, we do a similar thing. We create, we consider a sequence of guaranteed blocks, but then we increase the score of any guaranteed block that has a bigger block occur within delta of the guaranteed block. Okay, so in this case here, this guaranteed block had a big block occur within delta of it. For our upper bound on growth rate, we just change the score of the little block to the score of the bigger block. So these are two techniques, the delta interval deletion process and the small block increase process. Very similar.
Like using dual hash.
Yeah,
slide that earlier.
Good question. Yeah, the reason there's different sizes of block is because different blocks of different hash type may be assigned a different score, and that's where the different hashes come in.
Blocks of different hash.
May have a different score.
Different hash size. Different block sizes.
So hashes don't really have a size per se, but
No.
right. But
56 bytes.
yeah, but hashes do have a difficulty. There's a difficulty to like an amount of computational resources needed to produce the next block, right?
Yeah.
Okay, so
Now you're talking about two separate hashes.
yeah,
Use the same algorithms. SHA-256.
no. Not the same SHA-256 using different hashes. One of them could be SHA-256, but another one could be a different type of hash.
A different algorithm. What SHA-512?
Yeah, fair enough. When you say algorithm, you mean like a hash, right?
Yeah,
exactly. So where you get bigger blocks here is that in the design of the protocol, you may decide to assign a different score value to blocks of different hash type.
What is the score value? How do you do it?
So there's a few ways you might decide to choose it, but for now, just think of it as it's something that you can decide into the design of the protocol. The reason you might want to make blocks of different hash types to be different score is because different hash types have different difficulties. And if they were all the same score, even if they're different difficulties, then sometimes what could happen is that one block type that's way easier to compute than another one may get all of the mining resources applied to that hash type, losing the advantage of of mining with different hash types.
But how do you define the threshold,
Like, how do you define what that threshold should be? Oh,
protocol currently defined.
oh yeah, okay, so
We check the threshold.
Yeah.
Every 2016 blocks, it resets the threshold. Or
yeah, okay. So there's a few ways that we've proposed to do what you're talking about is difficulty adjustment. That's the threshold adjustment.
Yeah.
There's a few ways we've proposed to do difficulty adjustment for merged Bitcoin. It's a very good question, very relevant.
There's a lot of stuff you haven't thought of.
Yeah, no, we have talked about that one. The approach that we suggest in our paper is that all blocks should have this roughly the same cost per block and the same score per block, or all blocks should have the same cost per unit score. Okay, they should be roughly equal. The cost per score should be equal to adjust the threshold so that the cost per score becomes somewhat equal.
Now, this is all still using the same SHA-256.
No. If blocks of different types use different hash types, SHA-256 is one hash type, but you could use a different hash type for
What?
ETH hash is another example. That's the hashing function used for the Ethereum proof of work before it converted to proof of stake. I believe it's ETH hash, but we can look that up. The reason, so you can look that up, feel free to. The reason they use ETH hash, according to online, is that the bottleneck for SHA-256 is the amount of specialized circuits you have that compute it. Whereas the bottleneck for ETH hash is number of memory accesses. So like, if there's a slightly different bottleneck for each of these hash types, then then it can induce different agents to decide to participate in the protocol in a way that's economically viable. And the idea of merged Bitcoin here is that, well, because SHA-256 is mostly centralized to those with specialized circuits, that damages the decentralization of the protocol. And it also, only those who have access to SHA-256 specialized circuits can economically viably participate in the protocol. You need to have your cost per hash to be about as low as it can get for you to participate. Whereas with other hash types like ETH hash, you just need to have a computer that can do memory accesses. And the bottleneck is just how many memory accesses that you use for it.
Would this be a fork of Bitcoin?
Well, I mean, everything is a fork of Bitcoin. Right, in a way, like Bitcoin's a fork of Bitcoin. Bitcoin is an algorithm for coming up with a consensus for what fork is canonical, right? But in principle, like, could this become part of the Bitcoin protocol? The answer is yes. And this type of thing has happened before. In fact, every time the Bitcoin algorithm has been updated, that results in a new fork of the Bitcoin protocol. And it usually requires consensus among miners and transactors that we're going to do this update. But you don't always get consensus. Sometimes there's a dispute between different sets of miners about what fork they're going to use. And this has happened many times before. And that's actually what things like Bitcoin Classic and Bitcoin Silver are, and things like that. If you've heard of these are actually different forks of the Bitcoin protocol, where there was a dispute about how the algorithm should change. The current Bitcoin, some things are not the actual classic Bitcoin because it comes from a fork that some disagree with. If I have my facts correct on that one.
So this would be a fully different one.
Well, not necessarily, because you can decide to make the Bitcoin protocol start to accept hashes of multiple different types going forward. And then, so you can start mining on top of the current Bitcoin highest score block with different hashes and saying, call that, if you want, just call it
We can.
Yes, yes,
They all have to get their code to run the same.
yes, yes. But that's happened before in Bitcoin. It happens all the time, actually.
When did it happen?
So during the creation of development of Bitcoin, there was a lot of proposals to how to make the code better. And
Yeah, that's true.
yeah.
The only real fork that ever happened was in 2015, when Bitcoin had some kind of flaw in its logic, and they had to roll back one of the blocks and then fork it to Bitcoin name and Bitcoin Cash, right?
Yeah, you're saying that's the only
That
real,
was September of 2015.
you're saying that's the only real fork. I'm not sure, like, maybe it depends on what you count as only a real fork.
Well, the only one anybody cares about.
Right, that's true.
I have Bitcoin back then,
But
and
there,
I was automatically granted a certain amount of Bitcoin Cash.
yes, exactly.
Right.
So that's an example of that occurring. I think we can think other examples of Bitcoin forking, but if it's not Bitcoin, there's things like Ethereum have done forking where you take the chain up to a certain point, and then this side here we're going to call Ethereum Classic, this side we call it Ethereum. And that does happen. But
Nobody participates in all this.
exactly. So
There's no lineage.
exactly. So
No nodes.
one of the reasons why, even though this is a completely decentralized protocol, you can still get this kind of consensus is because the market kind of decides what fork counts.
Yeah.
Whenever you start trading with, that's
Everybody agrees to use to run that code.
exactly.
Nodes in the line.
So there's a kind of like a social consensus mechanism that goes on with deciding what forks to use. Okay, so great questions. Oh, a few more slides left here. I want to make sure we get this done. Okay, so end result is that using those bounding techniques, we can get upper and lower bounds on the security region. Okay, we apply those, we can analyze them, we get these upper and lower bounds in the security region, and we can plot and simulate. We can plot the upper and lower bounds and then simulate the arrival process of the honest blocks here to, and we can see that the upper and lower bounds are fairly similar. Finally, to conclude, I think this is final. Wait, yeah, that's right. Finally, one thing that we can say about this is that if we set the difficulty setting, this is actually goes back to the question that you asked before. If we set the difficulty setting for each hash type so that the cost per block, which we'll call P1 and P2 in dollars per block, is the same, and we consider a case when network delay is very close to 0, then we can make the cost of attacking the Bitcoin protocol P1H1 plus P2H2, which we can prove is optimal. That is, no other protocol can cost more to attack than this.
And when you talk about that, this concept of network delay,
Yeah.
how do you define that? Is that the communication between the nodes when they propagate who's out there? How do you define that term?
So there's a question of how do you define it and how do you compute it, and how do you estimate a given a
You've got a whole
real?
bunch of nodes distributed globally.
Yep.
I don't know, what is it now? Is it 60,000 nodes the last time I looked? Worldwide?
Yeah. So generally speaking, when we talk about a network delay of delta in our analysis, we assume kind of a worst case network delay delta, and
But by definition, that network delay has to be less than 10 minute blocking.
it doesn't have to be, but it's good that it does. If it's greater than the 10-minute block interval, you're going to have a security. It's going to damage the security of the protocol.
Oh, the protocol just rejects them.
No, okay. Do we have a whiteboard I can explain to you? This is an actually interesting question. Yeah, okay. So if you have, by the way, I don't know if anyone's on our video streaming thing, but could you check just to make sure? Okay, so if you recall that one formula we had like lambda h, which is the fully delayed honest growth rate, is equal to h over 1 plus delta h. Check, right? This is right? Yeah, that's right. Okay. So if delta gets really, really, really big,
Yeah.
even longer than the average next block, this is still a number that's not zero. It goes to zero, but it's not zero down to 35. Delta gets really, really big. So what it would look like is it would be stupid. Now this would be stupid, okay? But you could theoretically do it. It would be a really, really, really big delta here, okay? And then in fact, you not only can you make delta bigger than the next block time, you can make it much bigger. You can make it 1,000 times bigger than the next block. And then what you're going to get is this is what's called another block. We're going to get a lot of blocks in that time delta that are just working. They don't see each other. They don't see this current block.
Yeah, so your protocol would just reject all of the open ones.
Yeah.
By that, you define it, you can code it.
Wait, if you define it, what do you mean by that?
Well, if it's exceeded a certain threshold, delay.
If it's exceeded a certain threshold of delay, yeah, just reject. Well, remember, like we want to distinguish between an analysis of an algorithm and what thing we're rejecting in analyzing an algorithm and what's actually rejected by the protocol. The rule for the protocol is that you always just run the typical longest chain. That's it. You know nothing about all the other blocks. All you do is just rely on the typical longest chain, right? So continuing on this, and if you had a really, really long like delay delta, way, way, way bigger than the next block by the baseline, then your chain is basically going to look something like this.
I'm just thinking of it in terms of the practicality. If you were running a node, a Bitcoin node, like I used to do.
Yeah.
Right? You know, I mean, if a block took longer than 10 minutes to arrive, you know,
Yeah. That's a very good reason.
Have you ever run a node?
I've not run Bitcoin nodes. I've run some other things nodes.
Yeah, I was just thinking from practice.
Yeah.
But I think we're bored.
So from a practical point of view,
The network delay is
well, the network delay is not actually a different nodes have different network delays, right? So, and you know, if you were a miner and then your internet got cut out for 20 minutes, your specific network delay is 20 minutes.
And you can see, yeah, so you would reject any blocks, right? You know,
Even if you had a long network delay of 20 minutes, like you can still mine on the prior block. That's fine. It's not like a miner never rejects a block. A miner only endorses prior blocks that money on top of them. Right? So you could have you could be delayed by like 100 or 2, delayed by 1,000 years of PP. And the protocol would still say you just mine on the tip of the longest chain that you see. That's it.
it doesn't make any sense.
Why not? So I mean,
Or you, yeah.
the block
Yeah, maybe let's
that's not
use it. Actually, there are some like measurement or experimental studies on this network delay. Like turns out to be just a few seconds, maybe 2 to 5 seconds.
I was just thinking in a 10-minute block video on the internet, we could send the signal around the world.
Yeah,
exactly.
Exactly.
That's why, like in the 2008 Bitcoin white paper, right? And Moto decided to use Bitcoin, because the guarantee this should be like much larger than that. This was the design choice. But nowadays, right? If you think about it, that was 2008, right? Now,
2009.
yeah. Oh, the white paper 2008.
Yeah.
The actual Bitcoin
It was 2005.
2009, early 2009. 16, almost like over 16 years by past. And today's internet is much fast than early 2009. That's why like the 10 minutes, right, this choice become a little bit too conservative right nowadays. Right. So in the future, someone should be okay. Another VIP requires improvement protocol. They want to like shorten this time. I would say this is possible. Now we know the fundamental reason. The security depends on the data versus the block in. Now, if data can be reviewed, and we can reduce the block interval. So the future, right?
Yeah, the thing to recognize the analysis involving these deltas here, for practical purposes in Bitcoin, the delta is so much smaller than like the next block that it's kind of irrelevant. It's almost negligible. But this analysis is very important for the design of blockchain protocols and the consideration of why don't we just make it with more blocks per minute, right? Wouldn't that be better? And the problem is that if you have more blocks per minute, then it reduces the security pressure.
More blocks per minute.
Or block rate, the block rate of the
Block
protocol.
interval, you want to reduce the block interval.
Yeah, if the block interval reduces too much, then it's
So
going
1 minute, right?
yeah, if it was that, then what eventually happens is that a bigger fraction of the honest nodes get forfeited. And then the economical chain. And so as you make block rate go faster and faster, you eventually increase the security threshold. So
Okay, that makes sense.
that makes sense.
Okay, good.
That's honestly the key part of the delta analysis is to kind of show what you can't do. Remember at the beginning I said, well, we showed you can't do this work, and well, this delta analysis is why you can't have why don't we just have 1 million blocks per second? Well, the reason is because I would have almost no speed removed. Because most of the blocks would just be working.
Yeah. Right. All of the nodes have to communicate within that block interval,
Yeah.
right?
A related story.
That's right, yeah.
Yeah, in the past few years, I would have been blockchain startup in Silicon Valley. They were so ambitious. They would like to push this interval from 10 minutes to 6 seconds. Not 1 minute, 6 seconds, right? You will have like project pushing the limit. That this like security analysis,
Yeah.
so important, right? That like when we did the calculation, we estimated the data should be like 2.5 seconds. Right? But the conclusion below 6 seconds. Yeah, okay, right? 6 seconds you can do it. This is the corresponding security analysis. So if we can remember one thing, I mean the usefulness of the security analysis is not only for today's Bitcoin, like maybe it's for futures Bitcoin and for other ambitious projects. They really would like to put to the new that, right? And we can tell them, oh, this is no 6 seconds okay, but if we further push it, I did the calculation from 6 to 5 seconds. You need to pay a large price in terms of security. You will suffer. So that we know why they should stop, why they should like price the correct bad, something like that.
Yeah. I should also say that, you know, the analysis of delta delay makes it a lot more difficult. It adds most of the complexity to most of this analysis. So anyways, I think we're done for time and everything. I could stay forever and answer questions for everyone. Some people arrived a bit later, maybe they want some subs or something. There's some food available. So anyone who came late and wants some more food, or anyone wants seconds,
There's lots of food.
there's lots of food available. So
Yeah,
please
yeah.
eat right now. I'm gonna go grab some food too.
If there's anything left, you can put it outside.
Absolutely.
Just do this like seasonal. They'll keep everything.
Yeah, there's some real pleasure. Thanks for all the really big questions. So that's a really attentive crowd, and I'm so glad we came in. I can chat some more about.
Yeah.
I don't
So
know. Some more stuff.
let's sign our speaker and then we can take it from that.
Well, thank you everyone for coming. So I'm gonna have more.